Hello, I'm Jace Holmes, and this is my Physics 2211 Lab 2 presentation. This lab discusses tracking a falling object's motion, predicting its velocity with gravity and drag, and including some discussion about what-if scenarios. This lab mainly talks about Newton's second law, specifically in the y direction. This equation works great for estimating, but not in the real world. In reality, we have other forces, such as drag. The drag force is pointing in the opposite direction as the gravitational force. Because of this, an object is not going to fall as fast as we really think it might. For this lab, I decided to drop a piece of paper. However, I folded this piece of paper to increase its drag force, while being able to fall stably. This is important because at terminal velocity, the gravitational force is equal to the drag force, therefore having zero acceleration and falling at a constant velocity. This relationship can be seen in the equations at the bottom of the slide. Using Tracker, I was able to track the object's motion as it fell. As you can see, it is initially accelerating and then proceeds to fall at a constant velocity. This is because all of the drag force acting on it. But for now, we will not focus on the drag force. Using some code in GlowScript, I was able to create a computational model for this piece of paper, not accounting for any drag force. My initial conditions include my piece of paper weighing about 3 grams, its initial height, which is about 2 meters tall, the gravitational constant of 9.81 meters per second squared, and a time of about 1 second from where I actually dropped the piece of paper in the video. Also, because I recorded the video at 60 frames per second, the change in time between each frame is about 0.017 seconds. Also for my video, I saw that the piece of paper hit the ground at about 3 seconds, which is when I stopped my loop. To calculate the force of gravity, we use Newton's second law. Force is equal to mass times acceleration. Additionally, using the velocity and position update formula, we are able to graph the motion of the piece of paper. However, this is hypothetical. As we can see, after about 3 seconds, it was supposed to reach around negative 20 meters. However, because I was just standing in my room, the piece of paper obviously did not fall 20 meters. Because of its flat face and its light weight, it was able to have a lot of drag force and reach terminal velocity at a really short time. This time can be seen when the velocity appears to be constant, or where its position is decreasing at a constant rate. So now looking at the graph with all three next to each other, it is clear that the drag force has an important part on determining the velocity and position of a falling object. And although a lot closer, the computational model with the force of gravity and the force of drag is still inconsistent with the actual tracker data. This could be partially due to something like camera angles when I was tracking the data, or maybe just an inaccurate prediction of the object's mass. When looking at the velocity versus time graphs, you can clearly see that in the gravity-only computational model, the velocity is constant, and in the gravity and drag computational model, the velocity is definitely not constant. At about a time of 1.4 seconds in the gravity and drag model, the velocity reaches an asymptote at a velocity of negative 1 meters per second, therefore, it is seen to be reaching its terminal velocity. If my piece of paper could be perfectly thrown downwards, it would reach its terminal velocity quicker. However, because it's just a piece of paper, the reality of being able to perfectly throw it is basically zero. This conclusion can be supported with a GlowScript model and just adjusting the code a little bit. By changing the initial velocity to about 0.7 meters per second downwards, it is clearly shown that the terminal velocity is reached about 0.1 seconds quicker. If I were to change the initial velocity to the terminal velocity of negative 1 meter per second, it would already be at terminal velocity, and therefore velocity versus time graph would appear constant. Because of this, I was curious, what if I threw the piece of paper faster than 1 meter per second? And, with just changing the code real quick, we are able to see that the piece of paper will decelerate to its terminal velocity of negative 1 meters per second.